Jai Hind all. Myself Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. Today in this video lecture, we will study about the digital system design, that is KEC 302, a very important topic, that is state diagram and state reduction techniques from third unit. So here the state diagram. What is a state diagram? A state diagram or a state graph, that is a pictorial representation of the relationship between the present state, the input, the next state and the output of a sequential circuit. Any sequential circuit that is depending on the previous state, the next state, what is the present input, what is the next output. So all these conclusions we are drawing on a diagram, and that is known as a state diagram. The state diagram is a pictorial representation of the behavior of sequential circuit. Now here the state diagram we can represent in two types, that is Mealy circuit and Moore circuit. So the state diagram, that means any system which can acquire any kind of state, that is state A. Let us say there are 4 states of a particular system, A, B, C and D. So we can represent the state switching by the state diagram. Let's say we represent the state diagram by two techniques. First is Mealy circuit and then we will discuss the Moore circuit. So here this is the Mealy circuit diagram, in which these circles are representing the states. So in this diagram, as we can see, there are 4 states, right? There are 4 states. Okay, the 4 states are A, B, C and D. Now, how to represent the input and output? So whenever, see here, whenever we give 0 input to the state A, the output is 0 and the next state is A. Okay. Whenever we give the state A as input 1, the output is 0 and next state is B. Similarly, whenever we give B as input 0, the output is 1 and the B remains in its own state. So that's why we have represented in like this. Okay. Now from next B to C, state switching from state B to state C. So here input is 1 and the output is 0. So input and output, they are represented on the line, and we are writing like, if we are writing 1/0, that means it represents the input 1 and the output as 0 on the line. So here, as directed line connecting a circle with itself indicates that the next state is the same as present state. If the arrow returns to its own state, then we call it as the circle returning to its own state. Now, the binary number inside each circle or the alphabet written in the circle, that is representing the name of the state. The directed lines are labeled with 2 binary numbers separated by a symbol. So the input value that causes state transition is labeled first, and the output value that occurs when this input is applied during the present state is labeled after the symbol. So here, now the state diagram, that we can also represent in terms of a state table. Okay. So whatever here it is, the state diagram, we can represent this state diagram into the state table. So present state is, we will write all the state A, B, C and D. And one more thing is that when the input is 0, when the input is 1, when the output is 0 and when the output is 1. So from present state to next state, whenever we are mapping from present state to next state, so always remember we have 4 types of combinations. Input may be 0 or 1, output may be 0 or 1. So we can make the table or transform the state diagram into the state table with 4 kind of representations. First is input may be 0, may be 1, output may be 0, may be 1, and the next state name. Okay. So here let us draw this particular diagram into the table, state table. So this particular representation is known as state table. If you are given this state diagram, then we can transform this state diagram into the state table. So here let us assume that present state is A. Now from A to B, the next state is B when input is 1 and output is 0. So from A to B, when input is 1 and output is 0. Input is 1 and output is 0. A returns to its own state when input is 0 and output is 0. When input is 0 and output is 0, A remains into its own state. Okay. Similarly, we can draw for another, that is switching from B to C. So we have B to C state, input is 1 and output is 0. B to C, input is 1, output is 0. B remains in its own state when input is 0 and output is 1. When input is 0 and output is 1, B remains in its own state. Similarly, C to D and C to C. So when input is 0 and output is 0, so C goes to D state. C goes to D state when input is 0 and output is 0. So similar way, all the transformations we can read from the state diagram and we can map into the state table, right? Now, state table is the tabular representation of the state diagram, representing all the input and output and state switching combinations. The present state designates the state of the flip-flop before the application of the clock pulse. The next state is the state of the flip-flop after the application of the clock pulse, and the output section gives the value of the output variables during the present state. So what we use in this sequential circuit is flip-flops. Whenever the clock pulses are applied, what would be the next state of the flip-flop? What was the previous state of the flip-flop, that is Qn, and the next state that is Qn plus 1. So here in case of sequential circuit, the state diagram and the state table are very important. So state diagram and the state table contain all the information and the representation, and we can use it for our convenience also. So one another type of representation that is very famous in that is known as Murray circuit. So in this Murray circuit, the little bit difference is there between the representation, that whereas we were representing input and output on the arrow, here only we will represent the either input or output. So let us assume when A remains its own state, when input is 0 and output is 0. When input is 0 and output is 0. Okay. So similarly, when we give input 0, D goes to A state. When input is 0, D goes to A state, and the output is also 0. Output is also 0. So the state of a memory element is specified by the value of its output, which may assume either 0 or a 1. So here there is a little bit difference between these two, that here we are representing input and output on the line. Here only we are representing the input on the line and output here. Okay. So whenever output is 1, the input to the C is 1. See here, input to C is 1. C remain its own state and the output is 1. Okay. So here when C goes to D state, C goes to state D, C goes to D, the output C goes to D when input is 0. See here, C goes to D when input is 0 and output is again 0. So here this output is 1 always whenever there is a transition. So state table, the state of the memory element is specified by the value of its output, which may assume either 0 or 1. So this is another kind of representation. The representations are same, and whatever is convenient to us we can use. We can either use the Mealy circuit or we can use the Murray circuit. Now coming to the state reduction. So there are various cases when the transitions are same, the state transitions are same, and the output and input both are varying, but they are indicating the same. So these redundant states and these redundant switchings can be removed. So here the state reduction technique basically avoids the introduction of redundant states which are repeating. That means the states, the transitions, the input and outputs, they are repeating and they are making the whole system as a complex one. So we are making all the possibilities in the state diagram, and we have an option to reduce the redundant state using the state table. Okay. So here there are in the diagram we are having A, B, C, D, E, F. So we are having 6 states. Okay. 6 states, all the transitions here, this is input and this is output. So we will write all the table. Let us assume we are writing for C and B. So C for next state, input x is equal to 0, x is equal to 1. Output maybe x is equal to 0, x is equal to 1. So we will make table between present state. Always remember the next state and the output. So if you are using this particular pattern, this is also okay. So I will suggest to you to use this pattern where the present state is known. Okay. Next state may be 0, may be 1 for and the output may be 0, may be 1. So input may be 0, may be 1 for next state and the output. So here we are taking the example from C to B. C to B when input is 0 and output is 0. C to B when input is 0 and output is 0. C to D, C to D when input is 1 and output is, let's say, C to D when input is 1 and output is 1. So we will write here C to D when input is 1 and output is also 1. So in this similar way, all the possibilities we can write in the state table, and after writing this in the state table, transforming all these switchings into the table, what we can do is we can identify the switchings which are exactly the same. So here we can see EF01, EF01, it is repeating. Okay. Similarly, BD01, BD01, this is also repeating. So now we need to see that what was the present state. So here what we can do is, let us identify for this one and let us see for this one. Okay. So present state is A, present state is C, the next state input output are same, right? So what we can do is, see here, A, B, D, F. So we will write here A, B, D, F. So what we have done, we have removed this one and we have removed this one. So because these two rows are exactly the same. So now if these two switchings are same, then we can obviously, we will take, we have given the first, we have taken this one, 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 and all the switchings are same. So we can write here A, B, D and F. Now coming to the A, B, D, 0, 1. See here, A, B, D, 0, 1. It's okay. Now B, B, F, 0, 1. We will write B, that is, see here, B to E, E to E. See here, these two are same, B, E, F, 0, 1. So what we have written? B, B, F, 0, 1. Why? We have replaced this E. Okay. Why? Because if I write B, E, F, 0, 1, then this state will be removed. So what is the option for this is that I will write B to B, B, F, 0, 1. So this is B, F, 0, 1. Because these two are exactly the same. Similarly, what we can do is for D, we will write EB 0, 1, D, B, B 0, 1. So why we are writing this D as B, B 0, 1? Because we have removed one state, that is E. We have removed the state E, and what we are doing is, in place of E, we are writing B. So wherever now the E is appearing, we will write it as B. So here this B, in front of B it is coming B, F, 0, 1, and for D it will come B, B, 0, 1, B, B, 0, 1. Similarly for F. Now for F, we will write F, C, 0, 1. There is no, there is no repetition at all. So we can write like this. So here we have removed this state E from the state diagram, and hence we can reduce the number of flip-flops. See, whenever number of flip-flops are taken or chosen according to the number of states and all, right? So state table and the state diagram. Similarly, one more example we can use for the reducing the state table. So here always we will write the state table. There are number of state, as we can see there are 7 state in the diagram. All next state and output, all the 2 possibilities we will write, and after writing it we can see that there are 2 states which are coming out to be, the identical, that is E, A, F, 1, 0. So I can replace E to G. So wherever it is E, I can write it as G. So whatever I will take, I will remove the next one. So here A, B, this is okay, this is okay. Now C. So E and G, either I will take this one or I will take this one, because these two are same. So E can be replaced with G. So I will write the reduced table in terms of either G or either E, depending on your convenience and on your choice. So I have removed here G. So A, B, C, D, E. A, B, C, D, E. Okay. Similarly, here next state and the output 0 and 1. A, B, C, D, E we have reduced to 5 state. One more state we have reduced, that is F. Why we are reducing? After removing this one, one state again it is coming common, and that is F. So we need to reduce this f also. So what is happening after we reduce one state, then next state may next again we can get two states to be similar, and then I need to remove one state from the state diagram or state table, and this process will repeat until and unless all the states and all the switchings are different with each other. So here this type of state table will give you the diagram in this way, and from the state table we can draw the state diagram like this. Now, what is the use of the state diagram, writing the state table? So here the application of the state diagram, and that is designing the counters. So coming to the counters, after discussing the state diagram and state table, there are two types of counters. First is asynchronous counters and second one is synchronous counter. So in the synchronous counter, number of flip-flops we are using, let's say for designing a counter we are using 4 flip-flops, then all the 4 flip-flops are given the same clock pulse for a synchronous counter, and in asynchronous counter, one flip-flop output will serve as next flip-flop as a clock. So the in asynchronous counter, flip-flops are connected serially, one by one. The output is connected to the clock pulse to the next flip-flop, then and so on. So that is the case for asynchronous counter, and the synchronous counter, same clock is being given to all the flip-flops. So what we can say is asynchronous counter can also be known as a ripple counter. In this type of counter, asynchronous counter, the output of the flip-flop is connected to clock of the next flip-flop. All the flip-flops are not clocked simultaneously. So design and implementation is very simple for so many number of states. So the only drawback is, since the output of the flip-flop is the clock input to the next flip-flop, so speed is an issue for the asynchronous counter, whereas synchronous counter, since they are running with the same clock pulse, there is no such issue with them. So all the flip-flops, since they are clocked simultaneously, so the speed is obviously high for the synchronous counters. That's one. Now coming to a very important concept which is used in designing the counters, that is the modulo of the counter. So here what we can say is, let's say I need to count from 0 0 to 1 1. So I will go slowly 0 0 to 0 1, 0 1 to 1 0, 1 0 to 1 1, right? So and maybe I can count downwards from 1 1 to 1 0, from 1 0 to 0 1, and 0 1 to 0 0. So I can count both up and down. So now these are the 4 states which my counter is taking: 0 0, 0 1, 1 0 and 1 1. So here the state diagram will come in picture. Whenever we are designing the counter, we will make the state diagram. So understanding the state diagram is very important. So next part is the modulo of the counter. So the number of states, see here, number of states through which the counter passes before returning to the starting state is called the modulus of the counter. So that means if I need to design 0 0 0 1 1 0 1 1 counter, then there are 4 states and the modulo of the counter will be equal to 4. So there must be 4 distinct states to say that that is the modulus of the counter. So here the number of states through which the counter passes before returning to the starting state is called the modulus of the counter. So modulus of the counter is the total number of distinct states, including 0, that a counter can store. Thank you.